Boarding. So 6.2 takes the area bounded by two functions, and now we are going to make it into a third dimension so that we can find the volume of a solid with cross sections. So similar to if we wanted to find area, we're adding up all of those rectangles, right? So we're taking and adding up heights essentially, multiplying by delta x. That brings us to the second dimension for an area. Now,
this is Assistant Principal, Mr. Johnson.
I did know about this.
At this time, please review your fire.
Okay, so volume, now we need to take all of these individual cross sections, individual shapes, and if I find the area of one with respect to either x or y, acknowledging that the size of them changes, and if I integrate or add up all of the areas of the triangles, that is what brings me to the third dimension of volume. Okay? So our formula looks very simple, and in this form, of course, it is. So we are integrating from limits of integration, sometimes left to right, sometimes bottom to top, of some area, and it's the area of the cross section that is in there. So the hardest part of this is determining what that area is with respect to the correct variable. So these are the steps. I'll read through them real quick, and then we'll get into the first example. So step one is you got to sketch the graph. This is like imperative that you get a rough idea what does the base look like so that you can then see top, bottom, left, right. All those things are still important, but the top to the bottom, if we're bounded that way with curves, that is the base of the rectangle, of the triangle, of the semicircle, or what have you. We find the formula for cross-sectional area, and then we integrate that to find the volume. Okay, so sometimes these pictures are given to us and sometimes they are not. This is our first example, and it gives us a good kind of tilted three-dimensional space so you can see what we're kind of looking at. The language of it: compute the volume, V, of the solid whose base is the region between the inverted parabola, y equals 4 minus x squared, and the x-axis. So that's the first thing that I would say that we would sketch. Right here. Okay? And then we have the x-axis. Okay? We always take a look at what the base is. What's lying flat? The next part. Vertical cross sections perpendicular to y. Okay? When I read perpendicular to y, I write parallel to x. That language is just easier for me to think about. I'm not thinking opposite, I'm thinking direct there. So my x-axis, of course, is my horizontal axis. So then I can see that my bases are running here, and I have an infinite number of cross sections coming up out of it. Okay? So as soon as you have that sketched, that's the most important part. You can have multiple cross sections if you want, but you're going to think about, if I'm looking at this, how do I slice it? So if it's parallel to x, it's a horizontal slice, because you want to actually get that semicircle. If I sliced it vertically, I would be cutting my semicircle in half. So it's a horizontal slice, and you draw that on your page. Like that. Okay? And this is what we need to find the area of. Once we can figure out the area of one of these, we put that formula into our integral. So area of a semicircle is 1/2 pi r squared. Our job is to figure out what the radius is, and the radius is not a number, It's with respect to the horizontal base. Okay. What is lying flat between my parabola with respect to my semicircle? What would I call that? Like, what's this? The diameter. Yeah, the diameter. So I don't want the diameter, right? I want the radius. So whatever that distance is, I would have to half it or think about it just one side, okay? And that's where the challenge really comes in this section, is sometimes you want that whole thing, and sometimes you want half of it. Sometimes when you manipulate the given equation, you already have half or all, and you need to either double or half. So there's a lot of moving parts which makes this challenging. That's the hardest part of this, is figuring out what is that dimension with respect to. Now, if it's running horizontally, that is an x equals value, right? That's an x number this way, which means we need to write our given equation, y minus 4x squared, y equals 4 minus x squared, I meant to say, as an x equals. So if I solve this for x equals, then I have the square root of 4 minus y. And I have to think about, does that account for the whole distance or half the distance? So this sketch right here is a little bit more clear and helpful. And sometimes picking numbers can help, picking an ordered pair to see what makes sense. Now, if I was solving this actually for values, I would put a plus and a minus, right? And that would be going both ways, making that the diameter. But because I'm not putting a plus and minus and accounting for two of them, actually the way I just solved it is my radius. So if I picked like 2, for example, for my x, then in this case I could figure out what my y would be. Or if I picked 4, whatever I picked, this relationship would hold true for this distance. So for example, if I picked, let's go with 2 for my y. Yeah, that's fine. So then it would be 4 minus 2 would be the square root of 2. The square root of 2 would be right here, which would be the distance that I would actually look for, okay? So in this case, it's a little bit more challenging because when you solve it, you're actually given what you want. And it's a little harder to think about, but this is my r. So from there, I just take my r, I put it into my area formula, 1/2 pi root 4 minus y squared. Simplify it. So the root and squared go away. So you have pi over 2 times 4 minus y. We take that and we put it into the integral. The pi over 2 can go out in front, but do not forget about it. Now is here where this is where I get all my finishing touches. I notice that I've got a y in there, so I need a dy for my notation. And if I have y's in here, I want y's as my limits of integration. This bounded my left and my right? My diameter or radius is bounded left and right. Now I need to bound it top and bottom with my numbers. And the other way, again, they're y's in my integral, so I need y numbers that would be plugged in that would make sense. So the lowest y value is 0. And the highest y value is the vertex, is the maximum of 4. We take that and we put it into our calculator. So go ahead and do that. And I'll take attendance while you are. You should be getting an answer of 12.57. And technically it's a unit cubed because it's a volume. Okay. right, so we're going to take a look at a few more examples. We should have time. So here's an example where there's no picture given. We're going to do everything start to finish. So find the volume of the solid with a base enclosed by x plus y equals 1 and bounded by the x and the y axis. So let's pause there and graph what we're given. So we have x plus y equals 1 and x and y axis bounding us. So it's a line, it's in standard form. You can graph it from there, or you can put it into y equals mx plus b to graph. That doesn't matter. So y equals negative x plus 1 would be the same thing. So I only need the first quadrant. I go from here to here, and there's my line. And then I'm bounded here and here. So my base is a triangle. It doesn't matter that it's a perfect triangle, but that's just what it is. So now, cross sections perpendicular to the y-axis, perpendicular to y, again, parallel to x, which means that the base is going to be an x equals. And they are semicircles again. So my slices run this way, and up out of them are semicircles. Okay, it's hard to get the drawing three-dimensional, but the main thing is the direction of the slice, and acknowledging that your semicircle goes from the y-axis across to that line. So if I needed to slice it and get one semicircle out, I would have to slice it horizontally, and then I lay it flat on my page. And whenever I do that, I make sure that the direction of my base here is the same as the direction of my base there, for my own understanding of whether this is an x equals or a y equals. So again, I have to think about, well, what is lying flat there? I have the diameter lying flat there. I don't want the diameter. It's a semicircle. Again, my formula that I'm looking for is 1/2 pi r squared. I need the radius. So I just want that. So again, it's x equals if it's going horizontally. That is an x number. So I take my equation and I rewrite it so it says x equals y minus 1. 1 minus y. That relationship is the diameter, though. X equals 1 minus y will take us from the y-axis over. Anytime you have an equation solved for one of the variables, it is the distance from the axis over in one direction to the graph. So when our graphs are symmetrical about an axis, we have to use caution there. Do I want to double it, or is it already perfect like the last one was? I only want half. If it were a rectangle on the last one, I would have doubled it. If it were a triangle on the last one, I would have doubled it. Because it was a semicircle, it split it in half just like I wanted it to do. So it's symmetry about an axis that we really have to look out for. Here, we still have to manipulate this because I've got a diameter right now. So I'm going to half that to get my radius. So A equals 1/2 pi 1 minus y over 2 quantity squared. It's up to you if you want to simplify this. You don't have to, but if you do, make sure you do it correctly, because this 2 inside here for the radius gets squared as well, so it becomes a 4. So if I simplify this, I really end up with pi over an 8 1 minus y squared. okay? So then in my integral is that, again, the pi over 8 can go out in front. I tend not to, because I just never want to forget about it. dy's at the end because I have y's in here. And now I go to my y-axis to see bottom to top number. So the bottom y number is 0. The top y number is 1. And this answer should come out to be very small, 0.131 units cubed. The section as we started is heavy on the perpendicular to y because we really haven't done them in that direction yet. But it doesn't mean that we won't go back to the other way. And in the worksheet and things like that, it definitely does. And I think that maybe one of my videos that I recorded last year has a couple of examples too, so I won't delete all those videos. All right, so this one again, find the volume of the solid with a base enclosed by y equals x squared and y equals 3. Now the cross sections perpendicular to y are squares. So we start by graphing the x squared and the 3. So parabola, parent function, and a horizontal line. Cross sections perpendicular to y, parallel to x. X equals are squares. So the area for a square is side squared. So parallel to x is a horizontal slice. And coming up out of there is a square, right? And we have an infinite many of those slices. So when I cut it and lay it flat, this is the side that is consistent with this. So our job, because we need this entire length, this entire side, we need from one side of the parabola to the other. It's x equals, so we have to take y equals x squared and solve it. X equals root y. But that will only represent half of it. Right? If we're talking about 1 and 1, but we would need the negative 1 to get my distance of 2. Right? Because this is symmetrical, I am going to double this to get the whole thing. And because it's a square, then I know the height of this, or the other side, is also 2 root y. Okay? So then my area is just 2 root y squared. So my integral would be 4y dy. And my limits of integration, again, I'm looking at y's in here. I go to my y-axis, bottom to top, 0 to 3. And that comes out as a nice round number of 18 units cubed. The other concept that is in this section is called the average value theorem, or the average value. This is exactly like your mean value theorem that you saw before. It's still saying the same thing. Secant equals tangent. It's still saying that from a different perspective. Okay? So average value, the formula as it's written, is 1 over b minus a times the integral from a to b of f of x dx. So if you integrate, right, the little f in there is a rate, is a derivative. If you integrate a derivative, a velocity, for example, you get a distance. And when you evaluate that integral, you're doing big F of b minus big F of a. Right? So change in distance, essentially. But average value then says divide it by the delta x, the b minus a. So you're still circling right back to a rate. This is still a rate, but it's an average instead of an exact at a moment. In terms of like context and the way that you use these, like literally the problems could be as easy as this. As soon as you see that phrase, average value, you just have to remember to put the 1 over b minus a out in front. It's what it's finding is the average height, average y value of the derivative graph. Or average rate, because that's what the derivative graph is. But it's finding the average y value from a to b of the derivative. It's adding up all those y values and dividing by the amount that you had. So the simple example right here is, here's your a, here's your b, here's your f. It's just 1 over pi minus 0, integral 0 to pi sine x dx. If you have a calculator, fine. If you don't, this is easy enough. You would have 1 over pi minus 0, or pi, times cos, negative cos, from 0 to pi. So it's 1 over pi times negative cos at pi minus negative or plus cos at 0. So you end up with 1 over pi times cos at pi is negative 1 and then negate it, so it's a 1. Cos at 0 is also a 1, so we get 2 over pi. The next several examples are just straightforward like this, so I'm going to skip them. and get to the theorem, which is saying very similar. So right, find the average value of the function on the given interval. You just plug it into the formula. These next two examples, slide 7 and 8. 9 and 10 gives you a little bit of context, gives you a little bit of a word problem. Okay, but you're still doing very, very similar. You're taking the equation, you're putting it into the integral, and you're doing from a to b, 1 over b minus a. And then we have this mean value theorem for integrals. So this is what I was saying is very much like the way we looked at it in chapter 3 and in chapter 4. So if f is continuous from a to b, then there exists a value c belonging to the interval ab, such that f of c is equal to 1 over b minus a integral a to b f of x dx. There is an instantaneous velocity that equals the average velocity. There is a tangent that equals the secant. It's saying the same thing, right? Because remember, little f is your derivative function. So f of c, we called it f prime of c back in chapter 3 and 4, equals, right? Remember, this is big F of b minus big F of a when I actually do the integral. So original divided by b minus a. This is your secant slope. Change in y over change in x. And that is equal to derivative at a moment. This is your tangent slope. It's saying the same exact thing. So this example here, let f equal root x. Find a value c from 4 to 9 such that f of c is equal to the average value of f on 4 to 9. So root x is our derivative. So we find the average 1 over 9 minus 4 integral 4 to 9 root x dx. And we say, well, when is that equal to root x? You may absolutely go to a calculator, math 9 this, and when we do, we get 2.53. Then conceptually, you just say to yourself, well, when does this average equal the derivative? When does it equal root x? All right, that's the question. So we square it, and we get that this happens when x is 6.42. And 6.42 is between 4 and 9. So that confirms that this is all true, right? Somewhere in this interval, the average equals, or the secant equals the tangent. Okay, so that's it conceptually for 6.2. So I'm going to stop the recording now.